today we're going to calculate and interpret second derivatives. So for the function y equals x cubed minus x, we want to find y of 2, y prime of 2, y double prime of 2, and y triple prime of 2. Okay, so what does y of 2 mean? Y when x equals 2. Yeah, so I'm just going to plug a 2 into the function, no derivative or anything. Y of 2 means plug into the original function, so that's 2 cubed minus 2, which is 6. So if I want to know y prime of 2, I have to have a formula for y prime of x. So what is y prime of x equal to? 3x squared minus what? 1. All right, then we plug a 2 into that. So we have y prime of 2 is going to be 2 squared is 4 times 3 is 12 minus 1 is 11. Okay, so here's where we get into new territory. Y double prime. Y double prime just means the derivative of the derivative. 6x. Yeah. So I've got the derivative is 3x squared minus 1. So the second derivative means the derivative of the derivative. So that is 6x. So y double prime of 2 is 12. Okay, and then I want to do y triple prime, which means take 3 derivatives. First derivative, second derivative, the derivative of the second derivative gives the third derivative, and that's 6. So what's y triple prime of 2? 6. Yeah, coincidence. So I'm just going to really briefly show you how to find y prime of 2 on your calculator and in GeoGebra. So in the home screen of your calculator, if you're using a graphing calculator, we're going to type nderiv, which is a function that you find in the math menu. So you just press math, scroll down until you see nderiv. It's number 8. Nderiv. And then we type the function, which is x cubed minus x, whatever function you want to take the derivative of, x cubed minus x, comma x, and that's just telling the calculator that x is the variable because the calculator's stupid, it doesn't know. Okay, so x cubed minus x, comma x, comma 2. Oops. Hit enter, and it gives us 11.000001. Because it's a calculator, it's doing this numerically. We know, because we know calculus, that y prime of 2 is actually exactly 11. So some of you have different generations of calculators. Some of them might be better and give exactly 11. But this is a useful thing to do for checking your answer, not for finding the answer. Right? And you can't, it will never give you a formula. Like you can never find 3x squared minus 1 using your TI. Right? It can find the slope of a tangent line at a particular point, but it can't find the function, the derivative function. All right, so let's do the same kind of thing in GeoGebra. Just want to evaluate the derivative of x cubed minus x at 2. F of x equals x cubed minus x. So I just graph that thing. And what I'm interested in is the slope of the tangent line at 2. So like here-ish. And my calculator, GeoGebra can just calculate that for you. It knows prime notation. You can type f prime of 2. And it gives you the output of 11. Very fast. So just 2 ways to use technology to get the answer that we already got using a little algebra. If you want to see other ways to get your calculator to find derivatives, you can work through the rest of these things later. We're just going to jump down to number 2 here. Notationally, after we take the third derivative, after we write f triple prime, all those primes get a little unwieldy right? You don't want to write like 18 primes if you want the 18th derivative. So after the third, we write higher order derivatives with a little number in parentheses. So this means the fourth derivative. All of these notations mean the fourth derivative. Okay, so now we're going to introduce a concept known as concavity. If a function can hold water like a cup, it's concave up. And if a graph looks like a frown, it's concave down. Okay. So looking at this picture, concave up or concave down? Up. Down. Both, yeah. Where's the switching point from down to up? 0. So we would say concave down on the interval -infinity to 0, and concave up on the interval 0 to infinity. And it's kind of vague whether you should include the 0 or not. Some books will include the 0 in both. Some books will not include the 0 in either, because it's kind of both there and it's kind of neither. Right? So I don't include it. I won't take off points for whatever you write. But that x equals 0 point is called an inflection point. Point of inflection or inflection point. Places where the concavity changes. All right, so when f prime is positive, this is a little review of what we've already discussed. If f prime is positive, what do we know about the graph of f? It has a positive slope, which tells you that the function is increasing. And no matter how you draw a function, right? If it's got positive tangent lines, positively sloped tangent lines, that function is going up. It's increasing. And if f prime is negative, then the graph of f is what? Decreasing. So look at this little picture I drew over here. Over here, we have negatively sloped tangent lines, and the function is decreasing there. All right, let's think about what happens when the second derivative is positive. I'm going to apply this rule that we just wrote down to the second derivative and the first derivative, because the second derivative is the derivative of the derivative, right? Okay, so if f double prime is positive, what does that tell you about f prime? It's increasing, right? If f double prime is positive, then f prime is increasing. And f prime represents the slope of the tangent line. So if the tangent lines are getting steeper and steeper and steeper, what is happening to the concavity? It's concave up. So just like in this picture here, I'll draw it again. Here my tangent lines are getting steeper and steeper and steeper and steeper. So that means f prime is increasing, which means f double prime has to be positive and f is concave up, as you can see. So if f double prime is negative, that means that f prime is decreasing. The tangent lines are getting less and less steep, right? So what does that tell you about the concavity? Concave down. F prime of x, yeah.
So the equation itself is what
at certain x values, yeah. It may not always be negative, but on certain intervals of x, yeah. So looking at this picture, drawn in pink here, if you look to the left side of it, my tangent lines are really, really negatively steep, and they're approaching 0, right? Tangent lines are really, really negatively steep and approaching 0, which means that the value of those slopes is actually getting bigger, right? Really negative towards 0. The value of them is actually larger and larger and larger. So that means that f prime is decreasing, which means that f double prime is negative and the graph is concave down. So these two statements here, super important. If the concavity of a graph changes at a point, then either f double prime must be 0 there or it's undefined there. And we call that a point of inflection, place where the concavity changes. Okay, I'm going to leave the details for you to work on, and I will be available to answer questions if you need it.